Hello, you're welcome. All right, so now we are going to be looking at work, energy, and power in physics. Okay, so that's three in one topic, right? So we're starting with work. So what's work, right? Work is defined as the product of force and distance, right? The product of the force applied and distance traveled by the object, okay, and of course, in the direction of the force. So which simply means that work, right, is a scalar quantity. Why? Because both the force and the distance, they are in the same direction, so there is no contrary direction. All right, it gives you a scalar value after you evaluate, okay, the product of force and distance. Okay, if that actually makes sense to you. But the SI unit of work, of course, is joule, right? So anytime you evaluate work, the SI units that represent work is joule. Now, as I already said, that work is a product of force and distance in the direction of the force. Now, there are some cases where, all right, the force is applied, okay, and of course, the force that's applied is not in the same direction with the distance. Let's say there's a force applied, and of course, the distance was supposed to be moved horizontally, okay, to let's say a distance of x, and the force applied is F, and that force is inclined at an angle of theta with the horizontal. Now, know very well that for me to evaluate work, both the force and the distance should be in the same direction. So, which simply means that I need to resolve this force for me to be able to evaluate the work, right, of moving this object horizontally from this position to this position, right? Okay, by pulling, let's say I use a string in pulling the object. So the force based on this string, all right, if I want to actually apply it in the formula of work, this force must be resolved. Why? Because the distance is horizontal. Of course, the force must be resolved horizontally, and of course, you know that for you to resolve force horizontally, okay, you are actually looking for the horizontal component of the force. When we treated vectors, we already know that the horizontal component of any vector quantity is always given as f cos theta. All right, f cos theta can also go to the vector tutorial to confirm that, of course, to uh, to actually look at the proof of this particular relationship, right? So invariably now, for this particular scenario now, where the force is inclined at an angle, and of course I need to evaluate the work. So the work is going to be equal to the horizontal component of the force, which of course is f cos theta, then times the distance, which of course the distance there is x. So I hope that is well understood. Okay, so we say if you are being given something like a body of mass 20 kg, right? Or let me make it simple. That's a force 20 newton, all right, is applied on a body, okay, and the force 20 newton is actually inclined at an angle of 30 degrees to the horizontal. So if this force actually pushes a body to a distance of let's say 20 meter. So the work is going to be equal to, of course, from the formula F cos theta, right, times X. So this is going to be equal to F 20 multiplied by cos 30, then times the distance 20 meter, right? I hope it's clear now. Okay, so now let's proceed. We are going to be looking at energy. All right, we've talked about work. We'll look at energy. Now, simple energy is actually defined as the ability, okay, to do work. That is the reason why energy and work shares the same SI unit, which is joule. All right. Now, energy is actually stored. Work is actually being performed. Let me illustrate that again. For you to actually do work, you must have energy. So the ability of you to do work means that you must have actually stored energy. Are you okay? So energy is stored, okay? Then of course, it is by the time the energy is exerted, okay, then work is done. Work is done, all right, when the stored energy is being exerted on something. All right. Okay. Let's take for example. Excuse me. Okay. You have fuel. Inside this fuel lies energy known as chemical energy. And this chemical energy, okay, it's actually stored in the fuel, right? Now, for this chemical energy to actually do work, right, you must actually probably you want to use it for a combustion. You want to burn something, or you want to create fire, right? Then you light it up, right? And once you light it up, then fire comes out. Probably the fire, it can be used to boil something or cook something or whatsoever. So this actually, the stored energy now comes out, and now it does useful work, right? So both energy and work, they are the same, all right? So they are interconvertible. I hope that's well understood. So now, energy is of different form, right? Energy stored is of different forms of energy. All right, energy can be in form of chemical energy, the one I've talked about. All right, you can see it in, of course, in petrol, fuel, even in wood. All right, it is stored there as a chemical energy. It is stored in a battery. All right, there's chemical energy in the battery. All right, etc., etc. There's also heat energy. All right, there's also light energy. Excuse me. There is mechanical energy. All right, etc, 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 etc. Now, we know that that's what is known as the law of conservation, the law of conservation of energy. All right, which actually said that energy can neither be created. All right, energy can neither be created, nor can you destroy it. Okay, it can neither be created nor can you destroy it. The only thing you can do is to convert an existing energy into a different form. And once you convert an energy in existing in a particular form to another form, all right, that is where works comes in. All right, so you can only convert energy from one form to another, and in so do you are doing work. All right, it can. So the law says that energy can neither be created nor be destroyed, but can be converted from one form to another. All right, let's look at typical example. Let's look at typical example. I think I've illustrated one. Let's say you have a battery. I needed to. This battery stores chemical energy. All right. Now, if you needed to get light, all right, all you just need to do is, first of all, you create electricity. The chemical energy stored in the battery, once you connect a wire across it, all right, causes electron to move to the wire to which creates electricity, right? So that means the chemical energy, first of all, is converted to electricity by connecting wire across it. Then from the electricity, now you connect bulb to the electricity that's generated. Then you have light. Okay, so that means this electricity wasn't created. It was gotten from the battery. Excuse me. And of course, the light energy wasn't created. It was gotten from the electricity, so it cannot be destroyed. In as much as this exists, this will exist. And someone will ask, then where is this one, the battery coming from? Then of course, every battery, the chemical energy, okay, is actually made up of some components, all right, that actually give rise to that chemical energy, all right. So the chemical energy comes from the chemical reaction that actually takes place, that brought about the chemical energy, right? If that actually makes sense. Let's also look at a situation where you have, all right, your mechanical generator, right? The one that gives light to you. It actually, once you rotate it produces mechanical energy. From mechanical energy, it's converted to electrical energy. Now this electrical energy now is actually used as a form of probably light or even heat when you connect your electric iron, right? So please take note of all this. Now, I'm interested in one form of energy, right? Which is very common, and that's mechanical energy. Of course, if we are actually describing mechanical energy, there's one thing that is very important for you to note, okay? Overall, for every mechanical energy, there is movement, there is motion, right? So any object that is under mechanical energy, that has mechanical energy, okay, actually creates motion. All right, but this mechanical energy is of two types. All right, one of it is kinetic energy. Excuse me. The other is potential energy. All right, so what is kinetic energy? Kinetic energy, of course, is energy possessed by a body that's already in motion. All right, the body is already moving. So a moving body has kinetic energy, right? But potential energy, okay, of course, okay. Let me describe kinetic energy, right? Well, so a body that is moving, all right, that's in motion has kinetic energy, and of course, the formula for kinetic energy, okay, let me use K to represent it, is giving us half mv square, half mv square. Of course, you know that the m represents the mass of the body, right? The v represents, of course, the velocity of the body. Okay, so now if a body is actually okay, if it possesses kinetic energy, all right, which simply means that it possibly is rotating or is moving, right, in any direction, and that movement from one point to another actually, okay, creates a work is being done. Okay, that's what a law known as work, all right, kinetic energy theorem. Work kinetic energy theorem. What do that theorem actually state? It states that, okay, a body that is actually that possesses kinetic energy does useful work only if there's a change in its kinetic energy, all right? Let's say when you measure the kinetic energy at the end, all right, at the final position, right, that's what the final kinetic energy, or better still, let me use K2, right, the final kinetic energy minus the initial kinetic energy is what actually leads to work to be done. And of course, that is very explainable when a body actually moves, all right, its speed actually changes. And for the speed of a body to change, we already know that according to Newton, right, a body possesses momentum when, of course, its speed changes, okay, with the constant mass with time. So if the speed of a body should changes, all right, from one speed to another speed, that object will have, all right, both final and initial kinetic energy, and because of that change, work is done. Remember, work has to do with, all right, a movement, all right, from an original position to final position, right? So work can also be given as, according to work kinetic energy theorem, the change in kinetic energy is another way of expressing work. So please take note of this. All right. Okay, having known this, then next we're now gonna look at potential energy. Now, potential energy, all right, unlike what you used to know, or some the kindergarten way of defining potential energy, which you were told that potential energy is the energy of an object of a body at rest. That is wrong. All right, that is a very what will I say, simplified information about potential energy. Okay, now if you want to define potential energy, okay, potential energy is the energy possessed by a body due to either its configuration, the configuration of the body, or its position, the position of the body in the space. Let me explain, let me illustrate this. A body has potential energy. Let's look at a typical example. Okay, based on position in the space, if you lift up a ball at a height, all right, and of course that ball is at a particular height and it's unstable. Why? Because probably what is actually holding it has the ability to actually to let it go. All right, then at this particular point where this ball is very, very unstable. Why? Because this height, this position, once this particular force that is holding it actually breaks, all right, this ball will not remain here. All right, it actually falls down to the ground. As such, we say that at this height, this ball possesses potential energy. That's one example. All right, and the example is based on configuration. Let's look at catapult, which of course is something you are very used to. Without stretching a catapult, it doesn't have any potential energy. All right, or probably without. But if you stretch a catapult and put a stone in it, once you stretch it, that configuration of stretching, okay, of stretching, which of course gives it an extension, all right, that changes its configuration, makes it, okay, actually causes it to have potential energy. Why? Because due to this stretching, if you leave it, all right, that potential energy will cause the stone that is in the catapult, okay, to move, to or to possess a kinetic energy out of the catapult, right? So you discover that potential energy doesn't just mean rest, okay, but it's a process where configuration, or of course or the position of the object, okay, prepares it for a motion which eventually is converted to kinetic energy. So please change your perspective about the information you already know, okay, for potential energy. All right, so now we are going to look at principle, okay, of different formula for potential energy, right? We're going to consider potential energy based on gravitational force, okay? So let's look at gravitational potential energy. So if the potential energy is based on, of course, gravitational force, simply means that that object probably is thrown either against gravity upward or is coming from gravity. Are you okay? So first of all, based on height, the formula for potential energy, okay, based on height is given as mgh. Right, let me use P, or better still, let me use U. Okay, U is common in most textbook. Okay, so potential energy U is given as mgh, mass times acceleration due to gravity times height. All right, but now let's consider something here. Let's see how potential energy actually relates with work. The same way I actually considered how potential energy relates, how kinetic energy relates with work. All right. Now, you discover that for an object to be thrown upward, right, it's going against gravity. Then, which simply shows that work is done against gravity. So the work done on that object is always against, is negative. Work is negative because it's against gravity. Meanwhile, the potential energy, okay, as it goes up high from this floor, increases. But from the height it's coming down, work is now positive. Work is positive. All right? And because of work is positive, the height actually reduces, which makes the potential energy to reduce. Because as height increases, potential energy increases. So height reduces, then potential energy reduces. Okay, so which means height and potential energy, they are actually opposite each other, right? So I can simply say that the work done is always negative, the change in the potential energy, minus change in potential energy. Okay, now we're going to apply something. Don't forget this. Don't forget this. Okay, so let's say in this case work is potential energy is u1 u2, right? That's going to be minus u2 minus u1. All right, now so for kinetic energy, work is k2 minus k1, right? But for potential energy, work is minus u2 minus u1. Now this actually leads me to what is known as the law of conservation of potential energy. All right, the law of conservation of potential energy. Now that this law actually states that, of course, the law of conservation of mechanical energy, please pardon me. The law of conservation of mechanical energy. Okay, so now this law states that, of course, as the normal law of conservation implies, all right, mechanical energy can neither be created nor be destroyed, right? But rather, there's always is converted from one form to another. And of course, we now have two types of mechanical energy, which of course is kinetic energy, okay, then plus potential energy. So let me use the symbol I'll be using, please. Kinetic energy plus potential energy. All right. So it said this can neither be created. So that means for a mechanical energy, there's always a conversion between kinetic energy to potential energy, and of course from potential energy to kinetic energy. All right. In a system that is exhibiting mechanical, okay, movement, or that possesses mechanical energy. All right. There is kinetic energy and there's potential energy, and two of them are interconvertible. All right. Now I'm going to explain in details. Let's see what happens when you project a ball at a particular height. At this point, all right, the height um the height of projection is h. Before you release this ball is not moving, so at that point it doesn't have any kinetic energy. So what is maximum here? What it has here is potential energy, right? U. The U at that point, all right, at the maximum height is maximum. But there's no kinetic energy. The K at that point is 0. But once you release this ball, all right, what happened? This potential energy now gets converted to kinetic energy. So at the point where there's an impact, where this object reaches the ground, hits the ground, okay, the final position, at that point the kinetic energy, all right, why? Because at that point, remember the velocity, as you throw an object down, right, the velocity is increasing because it's going for gravity. It's only when the object is going up that the velocity actually reduces. All right. So the velocity will be very maximum at the very point where it wanna hit the ground. All right. At that point where it hits the ground. So at that point where it hits the ground, the kinetic energy K is no longer 0. It's no longer 0. All right. It's no longer 0. Please pardon me. But at that point, it's maximum. All right. But at that point, at this particular ground, there is no height again. All right. That object doesn't have any height again. Then the potential energy U is 0. So that is the law of conservation of mechanical energy. Okay. Mechanical energy cannot be created or destroyed, but it is converted from potential energy to kinetic energy, of course, vice versa. So if I should actually state this in an equation, you now discover that it can also, you can confirm that using the equation that we treated originally, right? We have work to be minus U2, work equal to minus into U2 minus U1, right? And of course, work here is also is K2 minus K1. So work is equal to work. So I can simply say that, okay, the work based on kinetic energy done by the kinetic energy, which of course is K2 minus K1, is still going to be the same work that is done by potential energy, which is minus U2. All right, of course, if I should rearrange this equation, so I'm going to have K2 minus K1, right? Are we good? So open this bracket. This is going to be minus into U2 plus U1. Okay, so I want us to work on something. So I take minus U2 to this side, then minus K1 to this side. So gonna have K2 minus U2 comes over, it becomes U2 plus U2. Here I have U1, and K1 goes to the other side, it becomes plus K1. So you see what this is actually simply signifying. Okay, simply means that the sum of potential energy, all right, and kinetic energy is the same, okay, in a system from the initial to what? final. So this is the initial kinetic and potential energy, and of course this is the initial, right? This is the initial. K1 U1 K1 is the initial. This initial. All right, and of course this is final. So there's no change. Okay, so the sum of the potential and kinetic energy of a system is always constant, irrespective of the change that that system is actually undergoing. All right, whether the system is initially at a particular height, then you release it. Because there's a conservation of mechanical energy, the sum of kinetic energy and the potential energy of a system is constant, irrespective of the time or the transformation that that system actually undergoes. All right, so please take note of this principle of phenomenon. Of course, I will still apply it, okay, when we start solving our questions, examination questions. You get to appreciate all this, okay? So but just take it down and assimilate it. All right, so let's now talk about power. Let's talk about power. But I think we should actually look at a typical example, right? Should we? All right, let's talk about power first. Of course, power. Power is defined as the rate at which work is done. So that means the rate at which work is done with time. And of course, we know that it can also be defined as the rate at which energy is being dissipated. All right, because work energy, they are the same. All right, with time. And of course, the SI unit of power is watt. Okay, the same way that okay, that's by the way, let me just leave that. Now I can still express this formula in another form, right? Let me use P for power, right? Excuse me. We know that work is force times distance, okay? Force times distance. Okay, then divided by time. So if I should separate this, okay, force is gonna be some symbol. Will use the S can use R for distance. All right, and in some cases, to this formula is actually expressed based on integral value, but I don't want to go through all those complex process. All right, of course, if it is necessary, as we proceed, I'm gonna show you this. So what point am I trying to make? Force is work is force and distance all over time. Of course, you know that distance all over time is speed. All right, which of course goes speed and velocity. Of course, we use the same symbol, right? V. So power can also be expressed as force times speed. So please take note of that. So it's either you use this or you use this. Okay, let's say a situation where we are looking at the power. Power, okay, dissipated when an object of mass, let's say 10 kg, is carried to a height of 200 meter. and that actually happens in 20 seconds. So of course in this case now we are looking at the power, all right, dissipated for moving an object, okay, to a height, and that's actually entails that a potential energy is required, okay. So the power dissipated when a potential energy, all right, is being created by moving an object to a particular height, mg within the time t. Of course, you know that power is also giving us energy all over time. So this time around, that's potential energy, right? Okay, so we have mass being 10, right? Acceleration due to gravity is also 10. You know that already. Then multiply by the height, 200. And that happened in 20 seconds. So 2, because that's going to be 10 here. So at the end of the day, the power here is 10 times 10 times 10, that's 1000 watts, which of course is the same as 1 kilowatt. All right, let's see a question that deals with conservation. Conservation of mechanical energy. Let's look at okay, potential energy. Before I actually bring this question, look at potential energy, or call it elastic. Okay, elastic potential energy. Now, how do we actually get elastic potential energy, right? We actually get it from a material that is actually being stretched or compressed. For example, if we have a spiral spring, right? If you compress or stretch the spiral spring, all right, you discover that you are storing energy due to the stretching, right? And that energy is in form of potential energy. So for a stretch or compressed material, the potential energy, okay, is giving us half kx square. Good. Now, the kx square, of course, is the force constant of the spring. All right. The x itself is the displacement or the extension you created. So some book will give you E, right? So it's the extension you created by stretching that material. Okay. Now, remember, if you stretch a material, it stores potential energy, and if you release it, that potential energy is converted to kinetic energy, right? So for the law to actually hold, law of conservation, right? Half kx square can also lead to this potential, right? Potential energy will lead to kinetic energy, which is of course is half mv square. So a situation where you are being given such, all right, a phenomenon, okay, a question that actually relates these two, it is easy for you to actually find the unknown parameter, and that is exactly what we are going to be looking at, okay, in the next video. So we're going to look at the questions that relate with to all these information I've given you, and I believe that it will actually make more sense. All right, so see you in the next video. Thank you very much.